Welcome to an elementary synthetic geometry-based introduction to inversion of the real plane with respect to a circle course, episode 5, lecture 5. As a short survey of what we have learned and achieved so far across the previous 2 lectures, we have proved our first 8 theorems. And according to these theorems, we now know that under the inversion of the real plane with respect to a circle, under the positive power of inversion, every point that is the circle of inversion remains fixed or stationary, and when such a power of inversion is negative, then every point that forms the circle of inversion trades places with its diametrically opposite image with respect to the center of inversion, which means that either way, under the inversion of the real plane with respect to a given circle, the circle of inversion itself is taken back into itself. When the power of inversion is positive, then every point on the circle of inversion remains fixed, and in some sense, that circle of inversion does not undergo any transformation. And when the power of inversion is negative, then the entire circle gets moved or rebuilt pointwise in a non-trivial way, but such a rebuilding process still results in one and the same circle of inversion. We also know that according to our definition, the center of inversion is taken into the point at infinity, and conversely, the point at infinity is taken back into the center of inversion. And for the remaining points in the parent plane, we have the following situation. Every point that is located strictly inside the circle of inversion and that is distinct from the center of inversion, such a point is taken or thrown outside of the circle of inversion into a point that is distinct from the point at infinity. We know the formula. We know that all 3 points of interest must be collinear, and conversely, any point that is located strictly outside of a circle of inversion and that is distinct from the point at infinity is taken into a point that is located strictly inside of the circle of inversion and that is distinct from the center of inversion. And that means that under the inversion of the real plane with respect to a circle, technically speaking, the inner region of the plane that is delineated by the circle of inversion is somehow splattered all over the remaining parent plane, and conversely, the remaining parent plane is somehow crumpled into the inner region of the circle of inversion. And those of our viewers who are paying attention just about now, they are probably thinking, Roman, that means that according to the first 8 theorems that we proved, the area of the circle of inversion, which is a finite real number, pi r squared, is somehow stretched over the infinite area of the remaining or the complementary plane, the outer region of the circle of inversion, and conversely, something that is infinite or the area that is located outside of the circle of inversion is somehow crumpled back into something that is finite or the inner portion of the circle of inversion. And the question is, how is that possible when, intuitively speaking, something that is finite is stretched into something that is infinite, and conversely, something that is infinite is crumpled back into something that is finite? And this is a very good question. The answer to the question is out of the scope of this course, but a short answer to that question is the following. The one path that lies towards an answer to that question plows its way through the notion of the so-called notion of cardinality of a set, which sits on top of another notion, such as bijection from one set or between two sets, or one-to-one correspondence between the elements of two sets. And here the fact that we have to deal with something that is infinite already requires the introduction of a new mathematical notion, because the people who came before us tried and failed several times before they honed in on something that works, and that is something that works: the cardinality of a set and the corresponding bijection, or a one-to-one correspondence between two sets, which means that when a set is finite, then its cardinality is its size. And in this case, the notion of a size will not betray your intuition. The size of a finite set is simply the number of elements in that set. But when the set is infinite, then your intuition is guaranteed to fail you. The notion of a size no longer applies to such a set, and the way in which modern mathematicians deal with that whole situation is through the notion of cardinality, which sits on top of a bijection. And before we can technically tackle that answer to that question, how can something finite that can be mapped into something that is infinite, and something infinite mapped back into something that is finite, we have to understand and make peace with the following fact that was established again by the founding fathers of the so-called set theory. In other words, the cardinality of this set that is represented by the points of a unit line segment, or a segment of length 1, is actually exactly the same as the cardinality of the set that is represented by the points that form a unit square, or 1 by 1 square, which means that every point that belongs to a unit line segment, or a line segment of length 1, can be mapped to a certain point in the square that belongs to the square, and conversely, every such point that belongs to a square can be mapped back to a point that belongs to a unit line segment. But like I said before, this is out of the scope of our course. In this lecture, we will begin studying how inversion of the real plane with respect to a circle acts on slightly more complex geometrical objects, straight lines, and we will do so by proving our next 6 theorems, numbered 9 through 14. According to the theorem number 9, under the inversion of a plane with respect to a circle named C that has the point O as its center and R as its radius, any straight line L that passes through the center of inversion is taken precisely back into itself. Here in the statement of this theorem, the upside down symbol A means for each, for any, or just any, and this symbol over here means belongs to. So the fact that the point O, which is the center of inversion, belongs to a given straight line named L, means precisely that such a given straight line L passes through the center of inversion. Under these conditions, under the inversion with any power, positive or negative, such a straight line is taken into itself, and this is the statement of this theorem. And as we explained in season 1, episode 2 on this channel, is the moment you comprehend the statement of a given theorem, we suggest that you practice mathematics correctly, put this video on pause, walk away, try to generate your own proof. then come back and compare your ideas to ours. If you have a better proof, then by all means, share your beautiful and bright idea with our community. Meanwhile, we will proceed with a proof, starting with a positive power of inversion as shown over here with a plus r squared. Here in this case, we will need the following theorems that we proved in the previous two lectures: the theorem number 1, 4, and 5. Remember, for example, that in the theorem number 1, we proved that any point that is located on the center of inversion under the corresponding inversion with positive power remains what? Remains fixed or stationary. Again, don't forget that I have put together a free PDF file that sits in my free GitHub repository. The link to that file is in the description of this video or in the comment to this video. This PDF file gathers in one convenient place very succinct and short, crisp pictorial vocabulary or pictorial dictionary of all the theorems that we prove in this course. So you can always refer to this PDF file and quickly zoom in on the corresponding theorem and see at a glance what is going on with the statement of this theorem. But these are the three theorems that we will need for the case when the power of inversion is positive as such. Let a straight line L pass through the center of inversion O, and in that case we know that such a straight line will intersect the given circle of inversion C at two distinct points shown here and here. I did not give any specific names to these points in order to avoid the clutter and to keep the number of symbols to a minimum, but we all understand that, for example, this could be point X, this could be point Y, and when the straight line L intersects the circle of inversion C and the straight line passes through the center of inversion, then that straight line will intersect the circle of inversion at two distinct points such that the distance from the point O to the point X will be exactly the same as the distance from the point O to the point Y. Now in the theorem number 1, we proved that these points, let's say X and Y, will be what? They will be fixed or stationary. They will not go anywhere. Since these points actually belong to two geometric objects right now at the same time, the given straight line that passes through the center of inversion and the given circle of inversion, these 2 points will still belong to the same objects, the circle of inversion C and the straight line L. So when it comes to these 2 specific points under the inversion of the plane with respect to this circle, the integrity, the structure of the straight line, or more technically, the continuity of the straight line will not be violated. It will be one and the same. The straight line, when it comes to these points, X and Y, it will be continuous. These points still belong to the straight line L. Now, according to our definition, remember we agreed earlier that under the inversion of the parent plane with respect to a circle with any power, the center of inversion is taken into the point at infinity, and conversely, the point at infinity is taken into the center of inversion, and our plane is now called the extended plane because precisely it contains that one point at infinity, which in some non-intuitive and strange way smudged, so to speak, all over the parent plane. We remember that such a point at infinity in the plane is a planar image of the north pole of the Riemann sphere under the corresponding stereographic projection. But what that means to us is that prior to the inversion of the plane applied to it, the point O belongs apparently to the straight line L. And after that inversion is carried out and the points in the plane are shuffled according to the definition of this transformation, that point will be taken into the point at infinity. Point at infinity will be taken back into this point right here, the center of inversion. And that means, again, the point to which we refer as the center of inversion that belongs to the straight line L will still be here. It will be replaced by the point at infinity, but it will be replaced by the point at infinity. As such, the continuity, the integrity or the structure of the straight line will still be preserved. It will not be violated. So now we took care of three interesting points: the two stationary points where the straight line L and the circle of inversion intersect, and the center of inversion. The remaining points that form the given straight line L that passes through the center of inversion are taken care of by our theorems 4 and 5. What does that mean? That means that, let us say that any point, any sample point that is located strictly inside of the circle of inversion and that is distinct from the center of inversion will be taken, according to the statement of the theorem 4, outside of the circle of inversion into a point that is distinct, evidently, from the point at infinity. This is point A prime over here. And remember that according to condition 1, definition 1, all 3 points of interest, that is the center of inversion, the pre-image point, and the image point, must be what? They must be collinear. But remember that any two distinct points in a given plane determine or define a unique straight line, and in this case, if the point O and the pre-image point A belong to the straight line L, evidently, then what are the choices for the image point A prime? There are no choices. That point must belong to the one and the same straight line L. And conversely, if a point such as sample point such as A prime that is located on the straight line L logically to the left of the center of inversion outside of the circle, that point, according to the theorem number 5, will be taken strictly into the circle of inversion. That point will be distinct from the center of inversion, and all these 3 points, A prime, A, and O, again will be collinear. Again, the argument here is the same. The pre-image point A prime and the center of inversion determine, in some sense, one and the same unique straight line L, and that means that for the image point A, in this case, under the inversion of the plane with respect to the circle, there is no choice for its location but to be on the same straight line L. That means that, intuitively speaking, what we just proved is that let's say, the radius OX, in some sense, is taken into the ray that originates at this point X and runs into infinity, and conversely, anything, logically speaking, from the point at infinity and to its right up to the point X is taken back into this radius OX. Now, exactly the same situation and scenario applies to the points that are located, logically speaking, to the right or to the other side with respect to the center of inversion. According to the same theorem 4, any sample point, such as the point B, that is located logically to the right of the center of inversion O, and that is strictly distinct from the center of inversion and is located inside of the circle of inversion C, will be taken strictly outside of the circle of inversion into the image point B prime. That point will be distinct from the point at infinity. And what are the choices for the location of the image point B prime? Well, again, condition 1, definition 1, all 3 points, the center of inversion, pre-image, and the image points must be collinear, since the points O and B belong to one and the same straight line L. That means the point B prime must also be located where? On the same straight line L. And conversely, any sample point B prime, the pre-image point, located logically to the right or to the other side of these points with respect to the center of inversion, and strictly outside of that circle on the straight line L, by the theorem 5, will be taken where? Strictly inside of the circle of inversion C. That point will be distinct from the center of inversion, and that image point B will have no choice but to what? Belong to the same straight line L. Why? Because the points O and B prime, they define and belong to the straight line L, which means that the image point B must also belong to one and the same straight line L. Here, intuitively speaking, under the inversion of the parent plane with respect to a circle with positive power, again, we're discussing positive power right now. Intuitively speaking, the radius OY, let's say, is mapped or thrown outside of the circle into the ray Y to the point at infinity, and conversely, anything logically speaking to the right of the point at infinity that runs up to this point Y is mapped into the radius OY. But that precisely means that under the inversion of the parent plane with respect to the given circle C that has O as its center and R as its radius with positive power, almost all the points of the straight line L that passes through the center of inversion get moved or shuffled or shaken in a non-trivial way, except the points where the straight line L and the circle of inversion intersect, this point X not labeled and Y not labeled. But that means that the straight line L is still taken into what? It is still taken back into itself, as we claim in the problem in the statement of this theorem, and that covers the case when the power of inversion is positive. And in the next segment, we will look at what happens to such a straight line when the power of inversion is negative. When the power of inversion is negative, as shown in red over here, minus r squared, then the fate of the center of inversion, O, will be exactly the same as the fate of the center of inversion under the corresponding inversion of the parent plane when the power was positive, and I will not say these words. Again, you can consult the previous segment. That point is taken into a point at infinity, and conversely, the point at infinity is taken into the point O. Thus, the structural integrity, or more technically, the continuity of the given straight line L that passes through that point, the center of inversion, will not be violated, or that continuity will be preserved. There will be a point over here that will belong to the straight line L. Now, when that point, that straight line L, passes through the center of inversion, it will intersect, again, as we noted in the previous segment, the given circle of inversion C at two distinct points. This time I gave the specific names. These points are no longer anonymous. Let us say that our logically left point is X, logically right point is Y. The distance from the center of inversion to the points X and Y is exactly the same. XY is a diameter of the circle of inversion. Its length is twice the radius, and the length of the line segments OX and OY is precisely R. And in the theorem number 2, in this case, when the power of inversion is negative, we will need the following mix of theorems 2, 4, and 5. So in the theorem number 2, we prove that under the inversion of the parent plane with respect to the circle C centered at O with the radius R, the point X is taken into the point Y, and the point Y is taken into the point X, as shown over here. X goes into Y, Y into X. These points trade places with respect to the center of inversion. And what does that mean? That means that when it comes to the structural integrity or the continuity of the given straight line L that passes through the center of inversion, that structural integrity, again, is not violated. It is preserved. In that sense, the straight line is still continuous at the point X and at the point Y. These points are still there technically. They still belong to the straight line L precisely at these locations. And this takes care of these three interesting points: y, the center of inversion, and x. And the remaining points of the straight line L, when the power of inversion is negative or gets shuffled in a non-trivial way, we have to carefully analyze the situation, but it's not particularly difficult. Here, the same theorems, number 4 and number 5, come to the rescue. So let us say we pick a sample point, such as the point A, that is located, logically speaking, to the left of the center of inversion in this particular demonstration, and that is located strictly inside of the circle of inversion. It is distinct from the center of inversion, and that point belongs precisely to the straight line L. Then, according to the theorem number 4, that point will be thrown out into a point A prime, such that the point A prime will possess three properties, which are what? First, that point A prime will be located strictly outside of the circle of inversion. Number 2, that point will be distinct from the point at infinity. And number 3, that point will belong precisely to one and the same straight line that houses the center of inversion and the pre-image point A. Again, the argument is the same argument that we used in the previous segment, because two distinct points define a unique straight line if the center of inversion, O, and the chosen pre-image point A are on the straight line L, then the straight line, the image point A prime has no choice. There is no wiggle room. According to condition 1, definition 1, that point must be collinear with the center of inversion in the pre-image. But here we notice what? There is another property over here for the point A prime, that if the pre-image point was logically to the left of the center of inversion, then the image point A will be logically to the right, which is to say that according to our definition number 2, when the power of inversion is negative, the center of inversion is in between the pre-image point and the image point. And conversely, if we pick any point A prime that is distinct from the point at infinity, that is strictly located to the right, let's say logically to the right of the center of inversion, and on the given straight line L, then according to the theorem number 5, this point will be thrown into the point A that has three main properties, or if we want to be pedantic, 4 properties, which are what? That point is distinct from the center of inversion. Number 2, that point will be is located strictly inside of the circle of inversion. Number 3, that point will be on the same straight line L on which the center of inversion and the pre-image A point prime is located. And property number 4, it will be on the opposite side of the pre-image point. It will sit logically, in this case, to the left of the center of inversion. And intuitively speaking, loosely but under a fairly tight artistic license, what does that observation mean? That observation means that let's say the radius OX, this radius under the inversion of the plane with respect to the circle C centered at the point O with the radius R with negative power, is mapped or taken into where? Into the ray that has its origin at Y and runs into the point at infinity. And conversely, loosely speaking, everything to the left of the point at infinity, the far end of this ray, and up to the point Y, is thrown inside the circle of inversion into this radius OX. And in the same fashion, we deal with the points, sample points, let's say P, that are located strictly inside of the circle of inversion, distinct from the center of inversion and on the straight line L. According to the theorem 4, such points will be taken where? Into the point P prime that will have 4 properties. Such a point will be distinct from the point at infinity. It will be located strictly outside of the circle of inversion. that point will be on the other side of the center of inversion with respect to the point P, which is to say that the center of inversion is in between the pre-image and the image point P prime. And importantly, property number 4, that point P prime will belong to what? That point P prime will belong to our main character, the straight line L that passes through the center of inversion. Why? Again, condition 1, definition 1, all 3 points, the center of inversion, the pre-image, and the image must be collinear. And if the center of inversion O and the pre-image point P belong to that straight line L, then the image point will have no choice, no wiggle room, no negotiation. It must be on the straight line L. And conversely, by the theorem number 5, any point P prime that is distinct from the point at infinity located on the straight line L outside of the circle of inversion and technically, logically, to the left of the center of inversion will be taken into the point P that has the 4 properties that you should nail right away. That point P is distinct from the center of inversion. It is located strictly inside of the circle of inversion. It is on the other side of the center of inversion, logically to its right. And number 4, the important one, it still belongs to the straight line L. And that means that, again, somewhat carefully, but in a very straightforward manner, loosely speaking, but under a fairly tight artistic license, our radius OY by the inversion of the plane with positive power is taken where? It's thrown outside of the circle of inversion into the ray that originates at the point X, runs into the point at infinity, and conversely, that ray, or technically speaking, everything to the right of the point of infinity that makes up that ray that originates at the point X, is thrown into the radius OY, again, when the power of inversion is negative. And that means that in this case, interestingly enough, unlike the scenario when the power of inversion was positive and we had 2 fixed points, when the power of inversion is negative, there are no fixed points. Everything, all the material in the plane gets transformed or moved, or loosely speaking, shuffled, shaken in a non-trivial way. No stationary points in this case, no fixed points. X goes into Y, Y goes into X, O flies into the point at infinity, point at infinity flies back to us over here into the center of inversion. Everything to one side, every radius, let's say, that is located to one side of the center of inversion is thrown outside in the opposite direction, ray, and conversely. And the same thing applies over here. Every point between O and Y is thrown into this ray to the other side, and conversely, everything from here is thrown over here. So every point of the straight line L gets rebuilt point-wise in a non-trivial way. The entire straight line is shaken and stirred and rebuilt. However, it is rebuilt precisely back, interestingly enough, it is rebuilt precisely back into itself. And again, the theorems that I put together and that we're proving right now are not that difficult, but in my humble, unprofessional opinion, these theorems should actually be put together and the students should generate their own proofs of these theorems, because this is the only way to develop the feel of how this geometric transformation behaves and how does it act on the so-called primitive objects. First, we studied how the inversion of the plane acts on individual points. Now we're studying how this transformation acts on straight lines. And in the next 2 lectures, we will study how this transformation actually acts on circles. There is a lot of interesting material there, but the conclusion of our theorem is correct. And I showed it over here under the conditions specified when a straight line passes precisely through the center of inversion, then be it the inversion with positive power, shown in blue over here, or be it the inversion with negative power, shown as in red over here, that straight line is taken back into itself. The straight line L is taken back into itself, and that concludes the proof of the theorem number 9. According to the theorem number 10, under the inversion of the parent plane with respect to a circle named C that has the point O as its center and the radius R under positive power, as is shown over here in blue with the plus R squared, when the power of inversion is positive, any straight line L that does not pass through the center of inversion and has precisely two distinct points in common with the center of inversion, named, for example, F1 and F2, is taken into a circle named Q that passes precisely through these 3 points: the center of inversion, O, and the distinct shared or common points F1 and F2. The circle Q, the image of the straight line L that satisfies these conditions under the inversion of the plane with positive power, is a circle that passes through the center of inversion and the distinct shared points F1 and F2. That is the statement of the theorem number 10 in symbols, and pictorially the essence of this theorem is shown on the left side of your screen here. The circle of inversion C is shown partially in white. We do not really need the entire circle. It's shown in white over here. The point O is the center of that circle and is the center of inversion. Any simple straight line L that does not pass through the center of inversion is shown in green. That straight line L is shown right here. That straight line and the circle of inversion C intersect at 2 distinct points. F1 is not F2 and F2 is not F1. Here is the sample point F1, here is the sample point F2, or the 2 distinct points over which or at which the given straight line L and the given circle of inversion C intersect. Under these conditions, when the power of inversion is positive, that is important, the power inversion is positive, the image of that straight line or that straight line is taken into a red circle named Q, shown over here in red, that passes precisely through the center of inversion and the shared or common points F2 and F1. This is the gist, this is the essence of the statement of the theorem number 10. We suggest that you try to generate a proof of that theorem on your own, and before you walk away from your computers, we also recommend that you may watch an animation that I put together using the free software called GeoGebra, and in the upcoming animation you will see a circle of inversion, you will see a small blue line at the bottom of your screen will run across a straight line. Of course, because we have hard physical limitations, there does not exist an infinitely sized computer monitor. You will see only a line segment over which a simple small blue point will run back and forth across the screen, but we suggest that you pay attention to the dark red image of that point, and specifically to the orbit or the trajectory that that image point will traverse. Again, you will see that that image will not be complete circle, red circle Q, again precisely because of the hard physical limitations. There does not exist infinite in size monitors, so you will only see a partial trajectory of the sample image point that will run across the straight line that does not pass through the center of inversion, but has exactly 2 distinct points in common with the circle of inversion C. And then after you watch that animation and reconcile the ideas of this theorem in your mind, you should, or we recommend that you walk away and try to generate a proof of that theorem on your own. Come back and compare your ideas to ours. And if you get stuck, then as a hint, as a first hint, we suggest that you may want to think about constructing a straight line called lowercase p that is perpendicular to the given straight line L, perpendicular to the straight line L, and passes precisely through the center of inversion. Those of our viewers in the audience who want to grow as mathematically inclined thinkers as time goes by should always, always, always try to run ahead of our curriculum in this course and try to generate all the relevant proofs of the theorems that we present on their own, and then compare their proofs to ours and solve all the problems that we will take on in this course on their own first, and then compare their solutions to ours. And of course, share your bright ideas with our community in the comments section. As such, one way to generate a proof of the theorem number 10 is to step as follows. First, as we suggested, construct a straight line shown in yellow, named lowercase p, that is perpendicular to the given straight line L, and that passes precisely through the center of inversion, the point O. That straight line, lowercase p, will intersect the given straight line L at a point, uppercase P, and once we have the point P constructed, once we have it on the books, the next thing that we do, the next step in our proof, is to reflect that point P in the given circle of inversion C with positive power into its image point P prime, uppercase P prime, shown in red at the bottom of your screen on the left. Again, this reflection, or that this inversion of the plane with respect to a circle with positive power, everyone in the audience should be able to carry out. We studied it in a detailed enough fashion. We know how to construct images of points. That was the subject of the previous two lectures. We know how to carry out that step, and precisely because everything, all the material that we have in this theorem is fixed. The center of inversion fixed, the radius of inversion, and thus the circle of inversion C fixed, the straight line L that does not pass through the center of inversion but has precisely two distinct points in common with that circle of inversion fixed. Consequently, the helper yellow lowercase p straight line perpendicular to L through the center of inversion fixed. What does it mean? The point P, uppercase P, where the perpendicular lowercase p and the straight line L intersect, fixed. Its image P prime, fixed. The distances OP and OP prime are fixed. Everything here is fixed, so the distance from the center of inversion to the image point P prime remains fixed for the duration of the theorem, meaning that given any fixed straight line, that distance will be fixed. What is the next step in our proof? Well, these are the steps that you're expected to generate on your own, and this is what amounts to the skill of generating a proof. Once we make one step, next step, next step, next step, and little by little we arrive to the end, to the original statement, and prove the theorem. The next step that we can carry out is the following. Pick a sample point on the given straight line L, that sample point named A at random or at will. That means any which point whatsoever. In that case, of course, the point A can coincide with the point P, but that is not interesting. We already took care of that. We already reflected the point P into its image P prime in a given circle with positive power. P is taken under the positive power of inversion into its image P prime, taken care of. What about the points F2 and F1, two distinct points over which the straight line L and the circle C intersect? Well, we already know how to deal with them. We already proved that these are the points that will remain fixed, stationary. They will not go anywhere. Under the inversion with positive power, the point F1 will be taken into the point F1. The point F2 will be taken into the point F2. Game over. Pick a random sample point on L named A. Let's say for the sake of argument, for demonstration purposes, that is located, the point, sample point A is located strictly inside of the circle of inversion. We just as well, we may pick such a sample point that is located outside of a circle of inversion. It does not matter. The logic, the beat, the flow, the texture of the proof is the same. What is the next step once we pick such a point? Exactly, we do to A exactly what we did to P. We reflect that point, sample point A, in the given circle C with positive power into its image point A prime. Where these points P prime and A prime are located in the parent plane, for now it's anybody's guess. It's not complete wilderness. We have some power of predictability for the locations of these points. And what is this power of predictability? Well, we have a fair amount of material, right? We have the positive power of inversion. We know our workhorse formula, and we know the condition 1 of definition 1. All the points of interest must be collinear. That means that the points O, the center of inversion, pre-image A, and the image A prime are collinear. They belong to one straight line. The points center of inversion, pre-image P, and the image P prime belong to another straight line, lowercase p. And what else do we know? This is the important bit. And in some sense, amongst this highly detailed information, try to see the fact that this straight line, the helper straight line perpendicular lowercase p to L through the center of inversion, is the core of the heuristic template on which all the other proofs that relate with this material will be constructed. Just in some sense, remember that everything begins with this helper straight line P perpendicular to L through the center of inversion. Now we write down the workhorse formula, the condition number 3 of definition 1, that ties together the distances of the pre-image and image points in both cases, A and A prime, P and P prime. What is this workhorse formula? Well, the product of the distances from the center of inversion to the pre-image and image points in both cases is what? One and the same real number called r squared, and these products of these distances are shown here and here. But evidently this number is one and the same, and that means that we can, in some sense, omit it, equate this product to this product, and then we simply split this product as follows. OP, we keep it on the left-hand side of the equal sign, but we steal the product, the distance OA, and we move it from the right-hand side to the left-hand side over here. And on that side, on the right-hand side of the equal sign, we keep the distance from the point O, from the center of inversion to the image point A prime, the same. We keep this guy right here, but we steal this guy, OP prime, the distance from the center of inversion to the image point P prime, and we move it to the right-hand side of the equal sign in the denominator of these two ratios. You see, this is the basic idea of how this proof works. From the given relation into which the distances of the relevant points in the given case are locked, we extract an interesting ratio. And how does this ratio help us? Well, Now let's move from symbols to some visuals. In our case, when we pick the point A, let's say for demonstration purposes inside of the circle of inversion C on the straight line L, because of the way we constructed our helper straight line P, the triangle OPA will be what? It will be a right triangle, of course. This angle over here is, all these angles are right, and this is what Euclid actually states at the beginning of his Elements in front of book 1. All right equal, all right angles are equal. Now, the interior angle of this right triangle OPA at the vertex O, or the angle POA, is shared with which triangle? Well, for now we cannot say much about the triangle OA prime P prime, other than we have some interesting proportion going for the lengths of the corresponding sides. But we can definitely say that this interior angle at O of the triangle OPA is shared or one and the same as the interior angle at the vertex O of the triangle OA prime P prime. And what does that mean? Now, when we combine this fact, shared or common angle, and the lengths of the sides about that angle in two triangles are in the same proportion, what does that smell like? Exactly, it smells like Euclid's Elements, book 6, proposition 5, if I'm not mistaken. In this case, Euclid proves that the triangles at hand are what they are, similar. The triangle OPA is similar to the triangle OA prime P prime. The triangle OPA, the right triangle, is similar to the triangle OA prime P prime. In modern times, this will be said, I think it will be SAS, side angle side, the similarity criterion, side angle side. These triangles are similar, and this is another theorem in Euclid's Elements. In such similar triangles, we have the corresponding sides lie opposite equal angles. Now, if we go back to our triangle OPA, that triangle is right by construction, and in that triangle we have which sides? The sides OP and AP, they subtend what? They subtend the right angle. But the side OP in the right triangle OPA, OP corresponds to what? Which side in this proportion? To the side OA prime. And the side correspondingly from this ratio OA corresponds to which side in the triangle? OP prime, which means that the side AP corresponds to the side A prime P prime, which means that because these triangles are similar and the corresponding sides in the smaller triangle subtend the right angle, the corresponding sides in the larger triangle OA prime P prime also must subtend a right angle. That means that the magnitude of the interior angle at the vertex A prime of the triangle OA prime P prime must be what? Precisely, this angle is shown over here must be right also. That angle must be right. And the corresponding angles, for example, let's say this guy must be equal to this guy. That is not that important to us. What is important to us? The angle, the magnitude of the angle OA prime P prime is precisely pi over 2 radians, 90 degrees, or that angle over here is right. And because the point A was chosen at random, that means that there is only one orbit that the images of the point A, the points A prime, can traverse. And what is that orbit? Well, because remember our remark, the distance from the center of inversion to the image P prime of the point P, which we obtained, as I explained, straight line, perpendicular to L through the center of inversion, that distance remains fixed. And the image points A prime run or roam the parent plane in such a way that the angle OA A prime P prime remains right. What does it tell us? Well, exactly. By the corresponding theorem, some people know it as the Thales' theorem, and in his Elements in book 3, where Euclid develops the theory of circles, he also proves the similar theorem. The angle in a semicircle is always right, and that means, and that proves, that the set of points which are traversed by the image point A prime is precisely the circle that passes through what? That passes through the center of inversion O and the two common points, distinct points F1 and F2. Precisely again, if we move the point A into F, this is precisely where the image of that point will be under positive power. And if we move this point this way into the point F1, this is precisely where the image of that point will be, again, with positive, positive, positive power. This is essentially the proof. This is how we can generate a convincing statement that under the conditions stated, the conclusion flows. And we recommend that as a separate exercise, you try to go through the numbers or through this reasoning when the sample point, for example, B, is taken outside of the circle of inversion. Here, exactly the same reasoning will apply, the same proportions, the same conclusions, the ratios will be the same, the corresponding triangles will be the same, except that here we will have which triangle? BPO, and the triangle OB prime P prime. Why is that? Well, the distances from O to B and O to B prime will be locked into the same relationship as our sample point P, the same relationship. And these two triangles will share which angle? Well, they will share, this time they will share this angle right here. This will be one shared angle. So the lengths of the sides about the same angle of the same magnitude are in the same proportion. The triangles are similar, and if the triangles are similar, our triangle BPO is right. It means that the remaining triangle OB prime P prime must be right, and that means that the orbit of the points B prime must and can only be a circle that passes through the center of inversion and the given distinct points that are shared or in common between the circle of inversion C and the straight line L, F1 and F2. This completes the proof, again, when the power of inversion is positive. If you have any questions, then the comment section is open. Go ahead, ask. And if you still miss anything, again, in the comment section, there is a link to the free PDF file, which is the chapter in my free book, Inversive Geometry for All, on which this lecture, episode 5, lecture 5, is based. Now that we understand why the theorem number 10 is true and is correct, we can come up with a very straightforward algorithm for constructing the image of a given straight line under the conditions specified using nothing but the Euclidean tools alone, a straight edge and a compass. But before we do that, I want to make sure that all the viewers in our audience are on the same page. It may be intuitively obvious right away why the image of our straight line L that satisfies these conditions must pass through the distinct points that are in common between such a straight line and the circle of inversion, shown here F1 and F2. But it may be not so intuitively clear why that circle, why that image must pass through the center of inversion. And here, that conclusion follows again from the observation that we just made a few seconds ago, the Thales' theorem, or Euclid's Elements, Book 3, proposition I forget which one it is, but the one that states that the angle in the circumference angle in a semicircle in any circle is right. And that means that the only possible orbits of the image points A prime must be those points from which one and the same fixed line segment, remember fixed line segment O, P prime, is seen under the right angle. And what is that set of points, or what is that orbit? That orbit or that set of points is precisely the set of points that forms a circle that must pass through the point O, because O, P prime, is a diameter of that circle, from the circumference of which that diameter is seen under right angles. That is why that image, the circle Q, must pass through the center of inversion. And once we understand that, the algorithm that I'm about to show you is very straightforward. And do not worry about the mess on the board. This episode is based on the corresponding chapter in my free book, Inversive Geometry for All. The link to that chapter is in the comments section. Click, download, everything is free of charge, accessible, open to all. Look at that construction. I have the construction as a standalone unit of information, nicely presented, and in some sense, it actually also is a good idea not for you guys to run ahead of the course, like I said, ahead of the syllabus, and try to prove all the theorems on your own and solve all the problems on your own, but grab your favorite graphing software, whatever it is. I use the free software called GeoGebra, but you should grab, it's a good idea for you to grab any software package that you like, free graphing software, and trace all these constructions. Do carry out all the steps with the mouse and the computer. Click, click, click. Go through all the motions and do that yourself. And to some extent, these days probably nobody does it, unfortunately, but doing what our ancestors did, physical compass, physical piece of paper, physical pencil, physical straight edge. Here's an incredible simulation of my straight edge, and then carry out all these constructions again physically on paper, see how this works. So the constructive algorithm in this case, when the power of inversion is positive, and this simple straight line L does not pass through the center of inversion, but has precisely two distinct points, F1 and F2 in the set notation. These guys must be distinct, but for the pedants in the audience, let's say F1 is not equal to F2. Let's say this is our stipulation two distinct points, because pretty soon we will consider the case when everything is the same, but these two points merge into one and we have a tangent. So in this case, when the two points shared between the straight line L and the circle of inversion, see, are distinct in this case, then the algorithm for the Euclid tools only, a straight edge and compass construction of the image of the circle Q, are the following. Step number one: if we're given the circle of inversion, that means that we're given the center of inversion. We know where that point is. Consequently, step number one, construct a straight line, lowercase p, perpendicular to the given straight line L through the center of inversion. All these steps are totally doable with the straight edge and compass alone. Construct that straight line shown over here, P. You don't need anything else. Forget about the fact that this straight line intersects with the straight line L at the point P. We don't need that. Snap a line through the center of inversion perpendicular to L. Step one. Step one symbolically. Step one visually, graphically here. Step number two, pick any point, F1 or F2, it doesn't matter. Here I showed you the point F1, and bisect perpendicularly that line segment OF1, or you can do also bisect perpendicularly the line segment OF2, doesn't matter. Cut this guy in half or cut this guy in half, doesn't matter. Straight line B perpendicular to the line segment, let's say OF1, such that the point where they intersect, X, is equally distant from the center of inversion, and the common point F1 XO is equal to XF1. The distance OX is equal to the distance XF1. Game over. So first line, second line, and at this point we're home free. The perpendicular bisector B that we obtained in step number 2 intersects the straight line P that we constructed in the step number 1 over precisely one point. And that point is what? That point is called Q. That point is Q. The perpendicular bisector B of the line segment OF1 intersects the straight line P at the unique point Q. And what is Q? Q is precisely the center of the image circle Q that has radius what? Pick your favorite distance from the center of inversion to Q, or from Q to F1, or from Q to F2. This point is equally distant from all 3 points of interest. The center of inversion, the first shared point, the second shared point. Once that information is identified, the circle, the image of the straight line L, is uniquely defined. Snap a circle with that radius centered at the point Q. Game over. The image constructed, and this is the entire algorithm. For a proof, again, technically we have to generate a proof. I will leave it as an exercise to the audience, but once you carry out the construction, then you will know and you will argue from the fact that you have a circle, you have the Theosis theorem, you will know that this angle is right, you will know that this angle is right, you will know that the triangles are similar, you will construct the corresponding proportions that you just saw a few seconds ago, but you will roll them up in the reverse order into something times something is equal to r squared, and this times this is equal to r squared, and that is how you will generate a proof. We are done with the theorem number 10 almost, with one little caveat. Those of our viewers in the audience who pay attention, they hopefully see right away that the converse of this theorem is also true. That is, under the inversion of the plane with respect to a circle with positive power, any circle Q, if we take it as the pre-image, any circle Q shown in red that passes through the center of inversion and has exactly 2 distinct points in common with the center of inversion is taken into what? Exactly, it is taken into the straight line that does not pass through the center of inversion, but passes precisely through these 2 common points, F1 and F2, and we will look at a proof of that theorem in the future lectures. But for now, we will move on to the analog of the theorem number 10, but in the case when the power of inversion will be negative. According to the theorem number 11, under the inversion of a plane with respect to a circle named C that has the point O as its center and R as its radius with negative power, this time with negative power as shown with the red minus sign in front of the square of the radius of inversion, any straight line L that does not pass through the center of inversion and has precisely 2 distinct points in common with the center of inversion, the point F1, for example, that is not equal to the point F2, and a point F2 that is not equal to the point F1, is taken into a circle that passes through the following 3 distinct points. The center of inversion, O, still just like in the case when the power of inversion was positive, but this time this circle, the image of the straight line L, will pass through the points F'1 and F'2, which are the geometrically opposite images of the common points F1 and F2. Symbolically, I captured it here with the fact that the length of the line segment f1 f prime 1 is twice the radius of inversion, which is the same as the length of the line segment f2 f prime 2, which is also twice the radius of inversion, which is to say that both of these line segments contain the center of inversion, and this is the statement of this theorem in symbols. And on the left-hand side of your screen, I captured the technical essence of this theorem number 11 visually or pictorially. Again, do not worry if you do not catch some details of this proof. I have all the nicely laid out diagrams for the theorems that we prove in this course in the free PDF file. The link is in the comment section. Click, open a separate tab, look at the constructions, and you will see that in white over here I show the circle of inversion named C with the center O, circle of inversion with the center at the point O and the radius R, which technically I do not show, but it is there. A given straight line L is shown in green. It does not pass through the center of inversion, but it has precisely two distinct points in common with the center of inversion, the point F1 shown in green here and the point F2. Now, under the inversion of the parent plane with respect to the circle C, that straight line, when the power of inversion is negative, will be taken into a circle named Q shown in red, and that circle will pass precisely through the center of inversion. But this time it will pass through the point f prime 1, which is a diametrical image of the first point f1, diametrical image of the point f1, and the point f prime 2, which is a diametrical image of the second common point f2. Once the statement of this theorem is understood, again, we suggest that you practice mathematics correctly. You put this video on pause, walk away, try to generate a proof of this theorem on your own, then come back and compare your proof to ours. And in order to help you do that, we suggest that optionally you may watch the following animation that I put together using the free software called GeoGebra. Again, in this animation, we suggest that you pay attention to the runner point. There will be a point that will be running, a blue point running along a model of a straight line. Of course, we do not have physical infinitely sized monitors. That point will run along a line segment that satisfies exactly the conditions of the theorem 11. That line segment will not pass through the center of inversion. It will cut the circle C at two distinct points. And we suggest that you pay attention to the trajectory of its image, which will be shown, again, not the complete circle, of course, only a partial circle, precisely because there do not exist infinitely sized monitors. And once you convince yourself sufficiently that, yes, this is what is going on, try to put this video on pause, walk away, and generate your own proof of theorem number 11. Observe that in a grown-up mathematics fashion, what will happen over here is the following. We will try to reduce, always the mathematicians will try to reduce the proof of the next theorem to the previously proved theorems. And here, what choices do we have? Here we have the theorem number 8, which we proved in the previous lecture, and we have just proved theorem number 10. According to the theorem number 8, the inversion of the plane with negative power, which is the case in our case, is equivalent to what? Is equivalent to the inversion of the plane in the same circle but with positive power with the consequent rotation of the parent plane about the center of inversion by pi radians. This is the theorem number 8. We take that theorem, we plop it on top of the theorem that we just proved, the theorem number 10. And what did the theorem number 10 say? Well, in this case, we construct the circle that passes through the points F1, F2, and the center of inversion. And then what do? We rotate all this beautiful mess about the center of inversion in the parent plane by pi radians, and boom, we have our result. Game over, we move on. But as diligent students of mathematics, as mathematically inclined thinkers, we should never, at least initially, back away from an opportunity to generate a bespoke or custom-made, if you will, by hand proof of the theorem, forgetting about the pre-existing machinery, so to speak. See if we can do it. Can we do it in this case? Yes. And how do we do that? Well, this will help us with the coming up Euclidean tools only algorithm for constructing the image circle in this case when the power of inversion is negative. First, again, we snap a straight line, lowercase p, through the center of inversion, perpendicular to the straight line L. That step is exactly the same as was the step in the proof for the power of inversion positive, when the power was positive. That straight line P will intersect our given straight line L at the uppercase point P. And what do we do then? Well, we reflect that point in the given circle, but with negative power. By the corresponding theorems, this point P will be thrown outside of the circle to the other side of the center of inversion. That will be this point. And carrying out, I showed this manipulation symbolically here. The point P is taken into the point P prime under the negative power of inversion, pictorially here and here is the situation. And now we also, what kind of material we have to work with? Well, we have two usual suspects, the candidates that lie on the surface, the distinct point F1 and F2, the points that are common between the straight line and the circle of inversion. And we flip these guys too. We reflect the point F1 into the point F prime 1, and we reflect the point F2 into the point F prime 2 with negative power in a given circle. We proved the corresponding theorems, we constructed, we solved the corresponding problems, we feel confident, we know how to do it, we understand very well every manipulation, every step that we take. The point F1 goes into F prime 1, the point F2 goes into the point F prime 2. These are diameters of the circle of inversion as captured over here. Everything is wonderful. So now we have our interesting points. And what are we to do next? Again, we pick a point at random or at will on the given straight line L. Let's say this is the point A over here. What do we do with that point? Well, we reflect it in the given circle with negative power. And again, we prove the corresponding theorems, we solve the corresponding problems, we feel confident about that step, we know how to take nothing but the Euclidean tools, a straight edge and a compass, and flip the point A into its image point, A prime. Everything is wonderful. We connect the pre-image point A with the image point A prime. These points must be collinear with the center of inversion. That straight line goes here. That straight line, A prime, will intersect our perpendicular line P to L through the center of inversion. And what interesting situation will develop over here? Well, the interior angles at the point O over here, shown over here. In other words, the magnitude of the angle, let's say POA, will be exactly the same as the magnitude of the angle, let's say P prime OA. Why is that? Euclid's Elements, book number 1, proposition, look it up. Vertical angles have the same magnitude. What is the next step in the proof? Well, you already should be telling me, because now we take our two pairs of points, P and P prime and A prime, we roll them up into our workhorse relationship, condition 3, definition 1 of inversion. This is the the product of the corresponding distances is one and the same, r squared. Because that number is one and the same, we can omit it, put the equal sign in front in between these two expressions, and then partition them cleverly into the following ratio. The distance from the center of inversion to the point P over the distance from the center of inversion to the point A is in the same ratio as the distance from the center of inversion to the image point A prime over the distance from the center of inversion to the image of the point P or P prime. You see, this is the same ratio. Now, we have two triangles, OPA and OP prime A prime, that share, technically do not share, but they have the same by magnitude angle, and the lengths of the sides about that angle of the same magnitude are what? Are in the same proportion. OP, OA subtend this angle, and OA prime, OP prime, two sides subtend this angle. Vertical angles, the same magnitude, technically it's the same angle, and again, Euclid's Elements, Book 6, Proposition 5, if I'm not mistaken. In this situation, the triangles are again similar. The triangle OPA and the triangle OA prime P prime are similar. This is the ancient, if you will, equivalent of the modern side angle side for similarity of triangles, and in similar triangles by the corresponding theorem that Euclid proves in Book 6. In such triangles, we have the sides, the corresponding sides lie opposite equal angles. Here, in our case, we can again chase the angles down and prove that the side, for example, OA in our right by construction triangle OPA lies opposite the right angle, and that means that the corresponding side in the triangle OA prime P prime will be which one? It will be OP prime. That will have to lie about, opposite the right angle at the vertex A prime. Why? Again, just to make sure that everyone is on the same page. The side OP in the triangle OPA corresponds to the side OA prime in the triangle OA prime P prime, and the side OA corresponds to the side OP prime. There you go, game over. OA lies opposite the right angle in a similar triangle. The corresponding side, OP prime, must lie opposite the right angle. That means that the angle OA prime P prime must be pi over 2 radians, 90 degrees or right. And the question is, since the point A was chosen at random, what is the possible orbit of the image points A prime, from each of which one and the same line segment, fixed line segment, OP prime, is seen on the right angle? Well, the Thales' theorem, or Euclid's Elements, Book 3, where he develops the theory of circles, states that in any circle, the circumference angle in a semicircle is right. So that means that the only possible orbit, or the set of points which the image points A prime can traverse in the parent plane, is exactly the red circle Q prime that must pass through the point O, because OP prime is a diameter of that circle, and precisely that diameter is subtended by all the angles. If we care to, for example, throw more points A prime over here on that circle, they all will be such that from these points, the line segment OP prime will be seen under right angles. Construct more of these guys, right angle everywhere. It's always the same here. Again, this in general and fundamentally completes the proof. You can also consider the case when the sample point A prime located, for example, outside. But here again, you will construct a straight line through the center O, reflect that point with negative power, put it somewhere, look at the vertical angles again, and fundamentally the gist, the idea, the tactical maneuvering in this in all these proofs is what? A straight line perpendicular to L through the center of inversion. And this, in this case, we have, when the power of inversion was positive, we have a physically shared common angle. Here we have vertical angles. Game over. Construct the proportion, write down the workhorse impression for the inversion of the plane with respect to a circle, construct the proportion, make the conclusion, prove the angle is right. And once the angle is right, this is it. The length of the line segment OP prime is fixed. Everything else is fixed. So as the points A prime roam the parent plane, they must do so over the orbit that must be the circle that passes through the center of inversion, and the points F1 prime and F2 prime. And that proves the theorem number 11. And that means that we also have our algorithm for constructing the said image of the straight line L when the power of inversion is negative with Euclidean tools alone. That is, in order to construct the image of the given straight line L under the inversion of the parent plane with negative power with Euclidean tools alone, with a straight edge and a compass, we carry out the following 4 steps. First, we snap a straight line named lowercase p perpendicular to the given straight line through the center of inversion. That straight line P is shown here in yellow, and this is the only thing that we need right now, that straight line. Once we have it, as a step number 2, we construct a straight line. I called it F, through the points O and F1, but you can do it through the points O and F2 just as well. It doesn't really matter. That is the straight line F right here. That straight line will intersect the given circle of inversion at 2 points, 2 distinct points, and diametrically opposite points, the point F1 and the point F prime 1. As shown over here, F intersects C, the circle of inversion, at 2 distinct points, F1 and F prime 1. And as the step number 3, once we have that line segment O, F prime 1, we bisect it perpendicularly with a straight line B perpendicular to the line segment O, F prime 1 in such a way that the straight line B intersects the line segment O, F prime 1 at a point X, it doesn't matter, such that the distance from the point X to the point O is the same as the distance from the point X to the point F prime 1, that is to say in plain English. Cut the line segment OF1 into 2 equal parts and locate that point where the division of the line segment OF1 is done in equal pieces, and that straight line B will intersect over here the straight line P that we constructed in the first step at one point called Q. This point is shown over here. This is the algebra, this is the geometry, and that point Q is precisely the center of the sought after image of the given straight line L under the inversion with negative power. And all we have to do now, as the step number 4, is actually draw that circle centered at the point Q. Q thus constructed with what radius? Well, any 3 distances will do. The distance from the point Q to the center of inversion O, or to any of the images of the common points F prime 1 or F prime 2. That distance will be the same between all 3 points, so we snap a circle, and that circle is Q prime, Q, shown in red. Q, red circle, is the image of the given straight line L that satisfies this conditions under the inversion of the parent plane with respect to a circle with negative power. And again, a proof of this statement is left to the viewer as an exercise, but at this point I hope that everyone in the audience understands how they will proceed with that proof. Here we will argue from the fact that first we will construct that circle, and then we will use the fact that the angle from which the corresponding diameter is seen from the circumference of that circle will be right by the Thales' theorem. The angles will be vertical if we construct them like so. The angles will be vertical. The proportion in the triangles will be similar. In similar triangles, the lengths of the corresponding sides about the same angle are in the same proportion. So we will construct the same proportion and argue that this is exactly what we have. The point that was picked at random on the given straight line L will obey the corresponding workhorse relation for the definition of the inverse images under the inversion of the real plane with respect to a circle. And this concludes the construction algorithm in the case when the power of inversion is negative. And we will move on to the next theorem, Theorem 12, where we will move our straight line L further away from the center. And at this point in the previous theorem, we dealt with the case which was what the straight line passed exactly through the center of inversion. Now we moved it a little bit away to have two distinct points in common between the straight line and the circle of inversion. And now we'll consider what will happen when the straight line L has precisely one point in common with the circle of inversion, or when that straight line is tangent to the circle of inversion. According to the theorem number 12, on the inversion of a plane with respect to a circle named C that has the point O as its center and R as its radius with positive power as is shown over here with the blue plus sign in front of the square of the radius of inversion, any straight line L that has precisely one point in common with the circle of inversion C, which is to say any straight line that is tangent to the given circle of inversion C at, let us say, the point T, is taken into a circle Q that has the points O, the center of inversion, and T, the tangency point of the given straight line L with the given circle of inversion, delineating a diameter of that image circle. This is the formulation of this theorem in symbols, and the pictorial or a visual representation of that theorem is shown on the left side of your screen over here. The circle of inversion C is shown in white over here partially. We do not really need the whole thing, so a partial view of the circle of inversion designated with the lowercase c, letter C, is shown over here. O is the center of inversion. O is the center of inversion. The straight line L that is tangent to that white circle of inversion is shown in green. Here it is, the straight line L. And let us say that this single point that is in common between the straight line L and the given circle of inversion C is T. Evidently, the straight line OT, which is a radius of the circle of inversion, is perpendicular to the tangent straight line L. And under the inversion of the plane with positive power, we claim that that straight line L will be taken into the red circle Q that has the center of inversion O and the tangency point T, delineating a diameter of that circle, and that image circle Q is shown in red over here. And this is the gist and the technical essence of this theorem. If you understood the statement of this theorem before you try to generate a proof of that theorem on your own, we recommend that you spend a few seconds looking at another animation that I prepared for you using the free software called GeoGebra. In that animation, again, you will see a blue point running along a straight line that is tangent to a sample circle of inversion, and you will see the image or the orbit, the trajectory of the images of that point shown in red. Again, precisely because we do not have infinitely large computer monitors, the corresponding orbit shown in dark red will not be a complete circle as you see on the board over here, but it will be only a partial circle, but that still should give you an idea. And you should, at this point, we recommend that you put this video on pause, walk away, and try to generate the proof of the theorem number 12 on your own. A synthetic geometry-based proof that we have in mind is so straightforward that in some sense we can leave it as an exercise to the viewer in this case, but just to be thorough, let us talk about this proof together in more detail. In the ancient terms, in his Elements, Euclid, in book number 3 in proposition 16, Euclid proves that in the curvilinear angle, as he calls it, curvilinear angle that is formed by the given circle and the tangent L, it is impossible to ascribe another straight line that is also tangent to that circle at T. In modern language, we will say that a tangent to a circle is a limiting position of its second. So if the straight line over here is a tangent, then it's not technically a second, and a second is not a tangent. But the moment we have a tangent, all of this maneuvering leads up to one observation. If on the given straight line L we pick any point, such as the point A shown over here, distinct from the sole point that is common to the given straight line and the circle of inversion C, or the single tangency point between the straight line L and the circle of inversion C. That point will be located where? That point will be located strictly outside of the circle of inversion. And now we unleash the theorems and the problems that we solved when we constructed the inverse image of such a point. How did we do it back then in the previous lectures? Well, we snap a straight line through the pre-image point and the center of inversion, OA, boom. Then we construct a tangent to that circle, C, boom. But this time, instead of constructing it, we have a gift. The mathematical oracle gave that tangent to us and said, tell the story. What do you see? And this is what we see. What was the last step in that construction? The last step in that construction, when the power of inversion was positive, remember, it was not symmetric, we observed, and later on we came up with the symmetric solution. But with the non-symmetric solution, we simply construct a perpendicular from the tangency point T. Back then, if I'm not mistaken, we named it that point B, onto the straight line OA. And this is exactly how we construct that image. But what is the essence of that construction? And we proved all the consequent statements that we had to make. What is the essence? What is the tactically actionable fact that we extract from this construction? The tactically actionable and useful fact for us that we extract from this construction is that the angle OA prime T must be what? That angle must be right. And what does that mean? Well, essentially game over, and in some sense the proof is complete. Why? Because we pick the point A on the straight line L at random, distinct from the point of tangency T. And everything else remains fixed. The center of inversion O fixed. The radius of inversion fixed. Thus, the circle of inversion fixed. The straight line L fixed. The tangency point T fixed. The distance from the center of inversion to the tangency point fixed. But what does vary now? Well, what varies is the orbit, or the trajectory, if you will, of the image points of the given pre-image points as they move along the tangent straight line L. That orbit must be comprised of such points that from each such point, given all the other fixed material, that line segment OT, the fixed line segment that is delineated by the center of inversion and the point of tangency, must be seen under the angle that is right. And what does that mean? Well, that means that by the Thales' theorem, that means that if we have a point that sits on the circumference, such as the point A prime, and that angle, the corresponding angle, subtends a diameter, that angle over here necessarily must be right, which means that the conclusion of this theorem follows under the inversion of the plane with respect to a circle shown here with positive power. Any straight line that is tangent to that circle at the point, let's say T, is taken into a circle. The orbit of the image points, the trajectory that it can traverse must be a circle, such that the red circle Q, the points O, the center of inversion, and T, the tangency between the straight line and the circle of inversion, form precisely a diameter of the image circle Q. And now, once we understand that straightforward proof, we also understand that the algorithm for constructing the said image circle Q, in this case with Euclidean tools alone, with a straight edge and a compass, is especially pleasant. I do not branch out this Euclidean tools only algorithms into their own separate problems, because these problems very straightforward. Once we understand the proof for the corresponding theorem, then the consequent algorithm for constructing the image in the specific theorem is very straightforward. But in some sense, our viewers can treat it as an informal problem, and they should try to solve that problem on their own. That is, in order to construct the image of the given straight line that is tangent to the circle of inversion when the power of inversion is positive, we follow the following three very straightforward steps. Step number one, we draw a straight line through the points O and T. We basically connect the center of inversion and the point of tangency between the given straight line and the given circle of inversion. This step is captured over here in words, or symbolically, if you will, any which way you want to symbolize straight line through the given 2 points. Be my guest, this is it. Graphically, we show that straight line in green over here. That is the straight line that connects the center of inversion and the point of tangency between the given straight line and the given circle C. In some sense, our favorite here is my incredible simulation of a straight edge. This is the task for which the straight edge as a theoretical tool was born. Connect any 2 points, no matter how close or how finitely far these points are apart. Step number one. Step number two, bisect that line segment with the straight line B perpendicular to OT, such that that straight line B intersects the straight line that we constructed in the first step, OT, at a point, this is amazingly enough at the game over, at the point Q, such that the distance from that point Q to the point O, the center of inversion, and the point T, the tangency point, is exactly the same. Game over. Step number 3, this is when you bring it home and put the compass into the needle of the compass into the point thus obtained. We constructed it here over here with the yellow line B perpendicular. This line segment is equal to this line segment in length. We make sure that our bisection works, and now we put the needle of our compass into the point Q and snap a circle shown in red named Q. That is the image of the given straight line L that is tangent to the given circle of inversion C with positive power, with the radius. That is what? That is the distance between the point Q and the center of inversion, or the point of tangency. That doesn't matter. Again, for a proof, I will leave it as an exercise to the viewer, but here again, we already understand that here we will argue from the fact that we will first construct a circle as we explained in this algorithm, and then we will basically pick any point again on the straight line L that is outside, connected with the center of inversion, show that we have which triangles over here. Well, you can go pull up the our material, our proofs from the previous lectures. The interesting triangles here will be what? The triangle OA prime T, because it covers this distance from the center of inversion to the image, and the larger triangle in this case OTA, because this triangle carries as its hypotenuse the distance from the point O to the point A, which is the pre-image. We have the radius. Once you construct the proportions, the corresponding triangles will be similar. In similar triangles, the lengths of the sides about the equal angle. And what is the equal angle in this case? Well, these guys will share this angle right here. And once you construct this proportion, the radius of the circle C will pop out in the second, it will be in the second power, r squared, and thus this will complete your proof. Do not be lazy. We recommend that you still go through this exercise by yourself. Meanwhile, we will move on to the theorem number 13, which will cover exactly the same case, but in that theorem, the power of inversion will be negative. According to the theorem number 13, under the inversion of a plane with respect to a circle named C that has the point O as its center and the radius R, with negative power this time, as is shown with the red minus sign in front of the square of the radius of inversion, any straight line that has precisely one point in common with the given circle of inversion, which is to say that such a straight line is tangent to the given circle of inversion at, let us say, the point T, is taken into a circle Q such that the center of inversion, O, the point O, and the point T prime, that is a diametrically opposite image of the tangency point T with respect to the center of inversion, delineate a diameter of the image circle Q. And in symbols I captured the fact that the point T prime is the diametrically opposite image of the given tangency point T, with the fact that the length of the line segment T prime is precisely twice the radius of inversion, which is to say that the line segment T prime is a diameter of the given circle of inversion. This is the statement of the theorem in symbols. Again, remember that here we have the power of inversion as negative. Everything else remains the same, and the pictorial or visual representation of this theorem is shown on the left-hand side of your screen. The circle of inversion named C is shown in white this time completely, This is the circle lowercase c. The center of inversion, O, R as the radius. It is omnipresent everywhere. I do not show it, but it's always evident what that radius is. An arbitrary straight line that has precisely one point in common with the circle of inversion C is shown over here in green, the straight line L. This is the straight line that is tangent to the circle of inversion C at the point T. The point T is shown in green right here. And the image of that straight line under the inversion of the plane with negative power is the circle Q, shown in red over here. This is the circle Q, right here, Q, that has the center of inversion, O, and the diametrically opposite image of the tangency point, the point T prime, as its diameter, shown over here. So that circle, that image of the straight line L, when the inversion is carried out with negative power, passes through the center of inversion again, and the point T prime, which is a diametrically opposite image of the point T. This is the visual representation. Once you comprehend the overall technical idea of that theorem, again, we recommend that you put this video on pause, walk away from the computer, and try to generate a proof of that theorem on your own, then come back and compare your proof to ours. And before you do that, we also recommend that you spend a little bit of time watching the animation, an animation that I put together for you using the free software called GeoGebra. And again, in that animation that you will see in a few seconds, I will have a point, a blue point, running along a straight line that is tangent to the given circle of inversion. And I suggest that you pay attention to the orbit of the image of that blue point that is traced in dark red, again, because the hard physical limitation, there are no infinitely large computer monitors. You will only see a partial orbit, a partial trajectory of the image points that are reflections of the runner point in this circle with negative power. And once you comprehend what is going on in this case, we again suggest that you try to generate the proof of this theorem on your own first. Using nothing more than the apparatus of synthetic geometry, a way to generate a proof of the theorem number 13 is as follows. Just like in the previous segment, in the previous proof, we know that if the straight line L is tangent to the given circle of inversion C, that means that any point A taken at random on that straight line distinct from the point of tangency between the straight line L and the given circle C will be located where? That point will be located strictly outside of the circle of inversion C, again, either by ancient technology, Euclid's Elements, Book 3, Proposition 16, curvilinear angle, you cannot inscribe, read the proposition, study it a little bit. By modern terms, a tangent to a circle is the limiting position of a second. Consequently, precisely one point in contact, any other point that belongs to the tangent will be outside of the circle of inversion. What do we do next? Well, we reflect that sample chosen at random, point A, on the tangent straight line L distinct from T, under the inversion of the given plane in the chosen circle with negative power, again, we unleash onto that process all the theorems and problems, all the theorems that we have proved and problems that we have solved. We know that the algorithm that uses the Euclidean tools alone for the construction of that image is completely symmetrical. As such, that point A is thrown inside of the circle of inversion into the point A prime, such that what? Well, we go back to the definition of inversion of the real plane with respect to a circle. All 3 points of interest, the center of inversion, the pre-image point, the image point are what? They are collinear. They sit on the one and the same straight line. We also have the workhorse relation for the corresponding distances. Condition 3, definition 1, the product of the distances from the center of inversion to the pre-image and the image point is equal to the square of the radius of inversion. Now, once we draw a straight line through the tangency point and the center of inversion in such a way that that straight line intersects the given circle of inversion for the second time. The first time it will be here at the point of tangency. The second time it will be at the point T prime such that the size of the line segment T prime is twice the radius of inversion, or a diameter of the circle of inversion. Then what does that mean? That means that the straight line OA will fall exactly on the straight line TO in such a way that the corresponding angles, there will be 2 pairs of angles, they will be vertical. In this case, the smaller ones and the larger ones that I do not show. But that means that the magnitude of the angle AOT will be precisely the magnitude of the angle A prime OT prime. Wonderful. What does that mean? Well, the square of the radius of inversion can be unzipped into a product of R times R. And into each R we substitute the material that benefits us tactically. What is it? Well, the distance from the center of inversion to the point of tangency, bam, bam, and the distance from the center of inversion to the point T prime, which is the diametrically opposite image of the tangency point, OT prime. Radius, radius, R square, everything is absolutely legal. And if you guys want, I can even go as far as highlight this with R. This is also R. This is the beauty of this construction. And what do we do now? This is the one and the same number, R squared. We drop it, we put the equal sign between these two products, and then we hash the factors in this product into a nice proportion that benefits us tactically again. That is, we keep the distance from the center of inversion to the pre-image point A on the left-hand side of the equal sign. We steal this distance from the right-hand side. We drag it over here. And we take this guy, the distance from the center of inversion to the image of the point A prime, and we push it to the other side into the denominator. Thus, we have OT prime, the distance between these 2 points, OT prime divided by the distance between the center of inversion and the image point A prime. So we have a nice proportion that says something interesting about 2 triangles. The triangle OTA, which is right by construction, and some mysterious triangle OA prime T prime. We have the right to construct that triangle all day long. There is nothing mysterious or illegal going on about this construction. We can do it. It's perfectly fine. Right here. So what is going on here? Well, we have technically in this case when the power of inversion is negative, remember things get flipped. And here we do not have the angle that is sheared, but we have an angle that is the same magnitude as we proved earlier, these 2 vertical angles. Consequently, we have in this proportion over here basically the statement of Euclid's Elements, Book 6, Proposition 5, I'm not mistaken, that if the length of the sides of 2 triangles about the same angle or angle of the same magnitude are in the same proportion, then these 2 triangles are similar. This is the modern equivalent of side-angle side similarity criterion. And once we have that, we use the consequent theorem that Euclid proves that in such similar triangles, The corresponding sides lie opposite equal angles. So what are the corresponding sides over here? Well, the side OA in the triangle OTA corresponds to what? To the side OT in the triangle OA prime T prime, just by proportion. We read these correspondences off of the proportion that we constructed. And in our right by construction triangle, the side, the triangle OTA, its hypotenuse OA lies opposite what? The right angle. And the corresponding to that side in this triangle is the side OT prime, OT prime in that triangle. And then that means what? That means that there is no choice, no wiggle room, no negotiation. That side must lie against the same angle of the same magnitude, bam, right angle. That means that the orbit of the image points A prime under the inversion of the chosen inversion of the plane with negative power must be what? Must be a set of points from each of which one and the same fixed, in this case, radius of inversion, OT prime, must be seen under right angle. And what is that orbit? What is this locus of points? What is this set of points in the parent plane? Well, evidently that's the circle that has the line segment OT prime as its diameter, which is exactly what we claim in our theorem. And again, in grown-up mathematics, this is not how mathematicians will operate. They will try to capitalize on all the previously done heavy lifting. And in this case, we could have done the same thing. We could have used the theorem number 8 and the theorem number 12 and said which words. According to the theorem number 8, the inversion of the plane with negative power is equivalent to the corresponding inversion with positive power with a consequent rotation of the parent plane about the center by pi radians clock or counterclockwise. And we would have brought in the theorem number 12, where we proved the similar statement with positive power, obtained the image of the given straight line, and then we simply take that image and rotate in the parent plane about the center of inversion by pi radians, counter or clockwise, doesn't really matter, and boom, we have our result. Game over. But as budding and developing mathematically inclined thinkers and as diligent students of mathematics, we should never shy away from an opportunity to exercise in generating our own custom-made, bespoke or handmade proof from first principles. And this is exactly what we did with this proof. And now, once we have a proof of the theorem number 13, we can, in a straightforward manner, almost instantly come up with an algorithm using which we can construct the image circle Q shown over here under the inversion with negative power using nothing but the Euclidean tools alone, or a straight edge and a compass. Again, I do not branch out these particular tasks into standalone and formal problems because I hope that all the viewers of this course and all the viewers on this channel already caught on with the program, that you should try to treat these tasks as such, and try to solve these problems by yourself first, and then compare your solutions to ours and share your better and brighter ideas with us in the comment section. As such, using nothing but the Euclidean tools alone, a straight edge and a compass, in order to construct the image of the straight line L that is tangent to a given circle of inversion C when the power of inversion is negative, we follow the steps. First, we draw a straight line called lowercase p through the center of inversion and the given point of tangency. Shown over here in symbols, the straight line P through the points O, the center of inversion, and T, the tangency point. Both of these points are given, and that straight line P will intersect the circle of inversion C, the circle of inversion C, at two distinct diametrically opposite points T, which is the point T is given to us, and the point T prime that we construct using that straight line. That fact is captured symbolically with the following statement. The length of the line segment T prime is twice the radius of inversion. That is step number one in symbols. Step number one visually. Yellow straight line P through the center of inversion and the given tangency point, all the way until that straight line intersects the circle of inversion shown in white for the second time at the point T prime obtained. This is all doable again with nothing but, in this case, the straight edge alone. Step number two, we bisect the line segment that is now delineated by the center of inversion, the point O, and the previously constructed diametrically opposite image T prime of the given tangency point T, with the perpendicular bisected B, which is perpendicular to the straight line OT prime, such that that straight line intersects that line segment OT prime at a point Q, which is equally distant from the point T prime and the center of inversion. And this is construction step of our Euclidean tools only algorithm in symbols. This is the step shown in visual representation. The straight line B, perpendicular bisector. This line segment over here is equal to this line segment, and that straight line B will intersect the line segment T prime O at a point Q, which is basically what we want. Game over. We claim that the point Q thus constructed is the center of the circle, that is the image of the given tangent straight line L under the inversion with negative power. Thus, as the final step number three, we construct the circle Q that has the point Q, uppercase Q, as its center, and any of the following distances as its radius: the distance between the center of inversion and the point Q, or the distance between the diametrically opposite image T prime of the given tangency point T and the point Q thus constructed in the previous step. Lowercase q for the name of the circle, uppercase Q for its center. That step is shown over here. And again, I leave the proof of the fact that this algorithm is correct and does indeed produce sought after image when the power of inversion is negative to the viewers. And here you should have no problem, because you will in a way construct that circle Q by force. You will argue from the fact that the angle at the point A, the magnitude of the interior angle at the point A prime must be right by the Thales' theorem. You will construct the corresponding straight line, the image. You will prove that the triangles are similar because the angles are vertical, and in similar triangles the lengths of the sides about equal angles are in the same proportion. You construct that proportion. You will work in there the distance OT prime and OT. These two distances turned out to be what precisely are the radius of inversion. You will collapse the proportion, unzip it into one line, and the product of the distances from O to A, from O to A prime, will be precisely R squared. Game over. And this is it for the theorem number 13. And in the next theorem, as you might have guessed already, we will keep moving the straight line L further and further away from the center of inversion, and now we will completely break this love affair between the straight line and circle and study the case when a given straight line has precisely 0 points in common and hangs out somewhere further away from the circle of inversion. And we will analyze and discover what will happen in this case when both the powers of inversion are positive and negative. In the final theorem of this lecture, we move our favorite straight line, L, away from both the center of inversion and the circle of inversion in such a way that the two objects of interest, a given straight line L and a given circle of inversion C, have precisely 0 points in common. As such, according to the theorem number 14, under the inversion of a plane with respect to a circle C that has the point O as its center and a strictly positive real number R as its radius, any straight line that has precisely 0 points in common with the given circle of inversion C is taken into a circle Q which has the following two properties. That image circle passes precisely through the center of inversion, O, the point O in this case, and it has precisely 0 common points with the circle of inversion C. And in the upper right hand side of your screen, I used a somewhat fancy mathematical notation to relay the fact that the two objects of interest, a given straight line and its image, a circle Q, have 0 points in common with the circle of inversion by using the intersection symbol over here and the notation for the empty set, or two squigglies placed one next to each other. So this notation over here says that the given straight line L intersects with the given circle of inversion over the empty set, and likewise the given circle Q intersects with the given circle of inversion C over the empty set, which again means that these two objects have 0 points in common with the circle of inversion. From the statement of this theorem, it follows that that theorem holds true for both powers of inversion, positive and negative. And the only difference between these two powers of inversion is the location of the image circle with respect to the center of inversion. Namely, when the power of inversion is positive, as is shown over here with the blue plus sign, then the image of the given straight line L that has precisely 0 points in common with the given circle of inversion C is located, as is shown in blue, on the same side with respect to the center of inversion as the original straight line L. But when the power of inversion is negative, as is shown with the red minus sign over here, then the image of the given straight line L that has precisely 0 points in common with the given circle of inversion C is located on the opposite side of the original straight line L with respect to the center of inversion O. I did not name that center of inversion yet. The letter O will show up in a few seconds when we will start constructing a proof of this theorem, but it should be evident that this right here is the center of inversion, or the point O, and it is quite straightforward to construct a meaningful definition of the side of the object occupied in this case when the power of inversion is negative and is positive with respect to the center of inversion and related to the original straight line. All we have to do is construct another straight line, helper straight line, that is parallel to the given straight line L and passes precisely through the center of inversion, and that straight line will partition the given plane into two half planes. And with respect to the straight line, when the power of inversion is positive, then the image of the given straight line, the circle Q, will be located in the same half plane, and when the power of inversion is negative, then the image circle of the given straight line L will be located in the other half plane. And once you understand the technical essence of the statement of this theorem, we suggest that you put this video on pause, walk away, and try to generate a proof of this theorem on your own, and then come back and compare your ideas with ours. And before you do that, you may want to watch a short animation that I put together for you using the free software called GeoGebra, again with the understanding that in the upcoming animation you will see both image circles, in this case when the power of inversion is positive and negative, but these circles will be only partial, evidently because in the physical world we do not have infinitely large monitors. At this point, after we constructed and worked together through 5 proofs of similar theorems, you should be able to generate the entire proof of this theorem on your own. And for demonstration purposes, I will only go over the details of such a proof when the power of inversion is negative, and I will leave the generation of a proof of this theorem for the case when the power of inversion is positive to the viewer, but that proof is very transparent, and in some sense it will seep through our proof of this theorem precisely when the power of inversion is negative, because we already know one heuristic template that works, but being a diligent student of mathematics, you already know the drill that you're always welcome to invent, discover, generate, synthesize a new heuristic template or a new approach that will work for a family of theorems. Now, what is that heuristic template? That heuristic template amounts to first constructing a straight line named lowercase p that is perpendicular to the given straight line L through the center of inversion, which in our case is the point O. And that straight line lowercase p will intersect the given straight line L at a unique and only one point, which I named uppercase P, shown over here. This is the algebra and this is the corresponding geometry. That straight line P perpendicular to the given straight line L that passes through the center of inversion is shown over here in yellow. This is the straight line right here. This is the name, lowercase p. This is the center of inversion O. This time I assigned the name to that point, center of inversion, and that straight line P being perpendicular to the given straight line L that has precisely 0 points in common with the given circle of inversion shown in white, named C, will intersect that straight line at the point uppercase P right here. We know that's step number 1, and we already know that that will be precisely the step in the upcoming algorithm for constructing the image of the given straight line with Euclidean tools alone, with a straight edge and a compass. This is the first step of our heuristic template. And what is the second step? The second step of our heuristic template is to take that point, uppercase P, and reflect it into the corresponding point P prime with the corresponding power. When the power of inversion is positive, we may refer to that point as P prime plus with the subindex plus to reflect the fact that the power of inversion is positive. And when the power of inversion is negative, then we reflect the given point P into the point P prime with the subindex minus to reflect the fact that the power of inversion is negative. And based on the theorems that we already proved, we know what? We know that if the power of inversion is positive, then the image point P prime plus will be on the same side of the center of inversion as the given point. And when the power of inversion is negative, then the center of inversion O will be in between the pre-image point P and the image point P prime minus. That is the second step. Wonderful. What is the third step? The third step is to take any point on the straight line L that is distinct from the point P that we obtained in the step number 1. Any point A on the straight line L such that the point A is distinct from the point P. And then what? Then of course we reflect that point in a given circle under the given power. When the power of inversion is positive, again the same technology applies to the image of the point A. That image will be located on the same side of the center of inversion as the pre-image point, and when the power of inversion is negative, then that image point, A prime, in this case I do not distinguish in order to avoid the clutter, that point A prime will be located where? It will be located in the parent plane, of course, and it will be collinear with the center of inversion and the pre-image point A. But in this case, the center of inversion A will be in between the pre-image point A and the image point A prime. Wonderful. Now that we have that based on condition 1 of our definition 1 of the geometric transformation that we're studying right now, the inversion of the real plane with respect to a circle, the straight line that passes through 3 points of interest, A prime, O, and A, will in this case intersect the straight line, the helper auxiliary straight line, lowercase p, precisely because A was chosen to be at random but distinct from P. That straight line will intersect straight line lowercase p at the center of inversion, the way things work over here. But the angles of the two interesting triangles in this case at the vertex O will be what? Will be vertical, namely in the triangle OPA and in the triangle OA prime P prime, because here we can connect the image point A prime with the point P prime minus in this case and form a triangle. So in these two triangles, the magnitudes of the interior angles at the point O will be the same one and the same because these angles are vertical. I did not write it down on the board, but technically when you make your own presentation and when you generate your proof, you will write down that the magnitude of the angle, let's say POA, is the same as the magnitude of the angle P prime minus OA prime, because these angles are vertical. And what is the final step? Well, the final step, the last mile that we do, is we bring in the condition 3 of definition 1, and we write down our workhorse formula for the points that we reflected. In this case, the point A that is taken into the point A prime and the point P that is taken correspondingly into the point P prime. But if we want to conduct this proof at the same time, we will have to distinguish between the image of the given point when the power is positive and when the power is negative. The power of inversion is positive, the power of inversion is negative. Either way, the same relationship that ties together the distances of the pre-image and image points relative to the center of inversion will be the same. The product of these distances is equal to the square of the radius of inversion. But because this is one and the same real number, either way, we can equate these two products. And now we carve the factors in that product in a way that favors us tactically. And how do we do that? Well, we steal one copy of the distance from the center of inversion to the pre-image point A, and we move it from the right-hand side of the equal sign to the left-hand side in the denominator of the left-hand side over here. The distance from the center of inversion O to the point P, from the center of inversion to the point P, over, when it's divided by the distance from the center of inversion to the distinct from P sample point on the straight line LA here. This ratio will produce a real number that, amazingly enough, will be, according to our definition over here, exactly the same if we take the distance from the center of inversion to the image point A prime, O A prime distance, and divide that distance by the distance from the center of inversion to the image point P prime. Technically here it will be minus. I use the minus to distinguish the powers of inversion, but in this proof technically it doesn't really matter. This is what we have. A pair of distances divided will produce a real number, which will be one and the same when the similar pair of distances is divided. But now what do we have? The length of the sides of two triangles about the same angle, equal angle in this case. Here the triangles do not technically share that angle when the power of inversion is negative, but the magnitude of these angles are the same nonetheless. When the power of inversion will be positive, and that is a proof that you will be generating, here you will have what? You will have the point A prime over here, and here you will physically, two triangles, the triangles of interest, will actually physically share one and the same interior angle. But now in this situation, these two sides about the angle, the angles of the same magnitude are in the same proportion. Euclid's Elements, Book 6, Proposition 5, I'm not mistaken, or in modern terms, side, angle, side, side, angle, side, and then side, angle, side. These two triangles are similar. In other words, the triangle APO is similar, as we proved over here, to the triangle P prime minus A prime O. And according to our ratio over here, the side OP, the side OP of the triangle APO corresponds to which side? OA prime of the triangle P prime minus A prime O, and correspondingly the side OA, technically the hypotenuse of the right by construction triangle APO, corresponds to what? Corresponds to the side OP prime minus, in this case, that will be the side, this side over here of the smaller triangle P prime minus A prime O. And that means what? Because the triangles are similar, that also means that in similar triangles, the angles of equal magnitude have the corresponding sides lie opposite to them. As such, in the triangle APO, we have its hypotenuse OA lie against what? Right angle by construction, because this is how we constructed this triangle. The side in the triangle P prime minus O A prime that corresponds to the hypotenuse of our larger triangle here is what? Is to OA corresponds OP prime, OP prime over here, OP prime, and that means that that side in the similar triangle must also lie against what? Against the same angle as it lies in the similar triangle here, so against the right angle. And that means that the magnitude of the angle OA prime P prime, OA prime P prime minus here in this case, must be what? Must be pi over 2 radians or 90 degrees, or that means that the magnitude of this angle is, that angle is right. And because the point A was chosen on a given straight line at will, at random, to be distinct from the point P, of course, that means that the only orbit that the images of the point A can traverse in the parent plane must be comprised of a set of points from each of which the given line segment OP prime, as we proved, must be seen from must be seen under the right angle. And what is that possible orbit? Well, according to the Theorems theorem, the circumference angle in the semicircle is always right. So the angle, since the angle OA prime P prime minus is right, the point O is fixed, the point P prime minus is fixed, because everything else, all the other material over here is fixed except for the runner point, if you will, the runner point A. So in this case, the point O, the center of inversion, stays where it is. The point P prime minus stays where it is, does not go anywhere. What is the only object that has a couple degree of freedoms over here is what? Is the point A prime. But that point can only traverse this circle that has the line segment O P prime as its diameter, and consequently the conclusion of our theorem follows. The image of the straight line of a straight line L that has precisely 0 points in common with the circle of inversion, when the power of inversion is actually both positive and negative, will be a circle that must pass through the center of inversion O, as shown over here, because O is part of a diameter which is seen under the right angle from any image of the point A, and that circle will intersect with the given circle of inversion. The image circle intersects with the given circle of inversion over the empty set, which means it has no points in common with that circle. And again, that also follows from the theorem that we proved previously in our first lecture. If the point P is located strictly outside of a given circle of inversion, then its image, regardless of the power, positive or negative, is located strictly inside. Not on the circle, not outside, not anywhere else, but strictly inside. And that precisely guarantees that the image circle of the given straight line that has 0 points in common with the circle of inversion must also be completely contained or properly contained in the circle of inversion, and that is another way of saying that the image circle Q, whether the power is negative or positive, has precisely 0 points in common with the circle of inversion, as shown over here. And now that we understand the A proof of this theorem, we also right away realize that we have an algorithm for constructing the image of the given straight line L, which has precisely 0 points in common with the given circle of inversion, using nothing but the Euclidean tools alone: a straight edge and a compass. Again, because we constructed already 5 similar algorithms, you should be able to construct this upcoming algorithm completely on your own. There is no mystery. And as such, in order to construct the image of a given straight line L that has precisely 0 points in common with a given circle of inversion, shown in white C, using nothing but the Euclidean tools alone, a straight edge and a compass, we follow these 4 fundamental steps. Predictably, first, we snap a straight line through the center of inversion perpendicular to the given straight line L. We name that straight line lowercase p. We know that such a straight line will intersect our given straight line at a unique point, uppercase P. This is the algebra, this is the geometry of this Euclidean tools only construction. This perpendicular straight line through the center of inversion, O, is shown in yellow, lowercase p right here. This line runs right here, and it intersects the given straight line L that has no points in common with the given circle of inversion at a point uppercase P. Step number 2, we reflect the given point, uppercase P, obtained in the previous step in the given circle with the corresponding power, be it the positive power of inversion or the negative power of inversion, and we have all the corresponding theorems in this case that are needed for this construction, and we also carried out the corresponding Euclid's tools only construction in the problems that we solved in the previous two lectures. We know how to do that step with Euclidean tools alone. Step number 3. Once we have our points P prime plus, in case when the power of inversion is positive, and P prime minus when the power of inversion is negative, essentially the game is over, because we have a diameter of the future image circle of the given straight line L, and now all we have to do is carry out the step number 3. Bisect the corresponding line segment OP prime plus or OP prime minus with the perpendicular bisector named B, which will intersect that corresponding line segment OP prime plus or OP prime minus at the unique point Q prime or Q minus, such that that point Q plus or minus will be equidistant from the center of inversion, and the corresponding image P prime plus or P prime minus. And this is the fact that I captured on the lower right hand side of your screen symbolically. The distance from the center of inversion O to the point Q prime, Q plus or minus obtained in this step will be exactly the same as the distance from that point Q plus or Q minus to the corresponding image of the point P, P prime plus or P prime minus. Once these points are obtained, these points will be the centers of the image circles sought after. Q, let's say if we want to be consistent, Q plus will be the circle image of the given straight line when the power of inversion is positive. Q minus will be the image circle of the given straight line when the power of inversion is negative. The center of that circle will be correspondingly at the point Q plus or Q minus, Q plus or Q minus. And the radius of this circle shown over here will be precisely the distance shown over here. I made a copy of this line over here, but you essentially understand that half the distance from the center of inversion to the corresponding image, P prime plus or P prime minus, will be exactly the radius of the circle Q. And judging by the location of the image point, correspondingly, we will obtain the circles sought after. When the power of inversion is positive, our circle will be located in the same half plane as the parent, as the original straight line L. And when the power of inversion is negative, then the image circle Q, shown in red over here, will be located in the other half plane with respect to the original straight line L. That is the Euclidean tools only construction algorithm in its entirety. That is the complete description of this algorithm. It carries out it has a finite number of steps. They're all correct, and the images are obtained or nailed, if you will, with absolute certainty. For a proof of the fact that this algorithm, this construction, is indeed correct and produces the sought after image of the given straight line L that has 0 points with the given circle of inversion, you will argue, because I leave this the construction of that proof as an exercise to the viewer, you will argue precisely from the fact that you already have your circle, the image circle over here. Correspondingly, the angle between the angle under which the line segments OP prime, for example, minus, or OP prime plus are seen from the point A prime will be what? Will be right exactly by the Theosis theorem, you will snap a straight line through the center of inversion like this. You will obtain 2 points, A and A prime, and your objective will be to show that the point A prime is the image of the point A under the given inversion. How you will do that? Precisely like I said before, you will argue from the fact that you have a circle, right angle in the correct location. Your point P will be locked in into the following relationship with its image point P prime. The distance from the center of inversion to that point times the distance from the center of inversion to its image will be equal to what? Will be equal to the square of the radius. And through the similarity of the triangles, you will show that triangles are similar. The lengths of the sides in similar triangles about equal angles are in the same proportion. You will construct the proportion, unzip it, and construct precisely the sought after product, and you will show that the product of the distances from the center of inversion to the point P and P prime will be precisely the same as the product of the distances from the center of inversion to the pre-image point A and the image point A prime, which is R squared, and that will conclude your proof. Now that we're done with the study of how inversion of the real plane with respect to a circle acts on straight lines, we covered all interesting cases when the straight line passes precisely through the center of inversion, when it's unbuckled from the center of inversion but still has two distinct points in common with the circle of inversion, precisely one common point with the circle of inversion and 0 points in common with inversion. We will move on in the upcoming lectures to the study of how the inversion of the plane acts on circles, not on straight lines, but on circles. But before we conclude this lecture, I would like to present a short visual summary of precisely how the inversion of the plane with respect to a circle acts on our favorite straight line L. As a succinct pictorial guide of all the 6 theorems that we proved in this lecture, I put the technical essence of these theorems on the board over here in one place. It doesn't have to be pretty, but it has to be technically correct, and it is. And what do we see? Well, here is the pictorial guide for the theorem number 9, theorem number 10, theorem number 11, 12, 13, and 14. And if we inhale the visual imagery, the visuals of all these 6 theorems, then what do we see? Well, we see that except for the most perhaps trivial case when the given straight line shown in green in all these theorems, the pre-image object is always shown in green, straight line L, straight line L, straight line L, 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 and L. We see that if the image of a given straight line under the inversion of the plane with respect to a circle with either power, positive or negative, is a circle, then what? What is the commonality between all these interesting, barring the trivial case, theorems? Well, in this case, if the image of a given straight line under the inversion of the plane with respect to a circle with either power, positive or negative, is a circle, as shown in red in all the pictorial representations of the theorems that we proved in this lecture, these circles do what? They always, always, always pass through the center of inversion, always, regardless of the power, whether that power is positive, shown over here, or negative, is shown over here. The image circle, if that is the image of a given straight line, always, always passes, look at this, through the center of inversion. This is the observation that you were expected to do on your own. If we inhale all the visuals of these 6 theorems, then we will make that observation. And also, the viewers in our audience who are paying attention and who worked with the proofs, studied the way we generated the proofs for all these theorems, these viewers most likely already realized then the converse theorems of all the theorems in this that we proved in this lecture are also true. And what does that mean? Again, barring the trivial case when a straight line is taken into itself under the inversion of the plane with respect to a circle, which happens always when the straight line passes through the center of inversion. In all the other cases, the image of a given straight line is a circle that passes through the center of inversion. And that means that conversely, anytime we have a circle as our pre-image object that passes through the center of inversion and has this interesting mutual juxtaposition with respect to the circle of inversion, then necessarily the image of all such circles will be what? Will be the correspondingly positioned straight line. In other words, in the next lecture, I will go over a proof of one such theorem in all the gory details, and I will leave the proof of the remaining theorems for the viewers. So as an informal homework assignment, once you comprehend everything that is going on in this lecture, before the next lecture begins, before you attend the next lecture, you may want to think about how would you prove these converse theorems. For example, one such theorem will state that if a pre-image circle, shown over here in red, passes through the center of inversion and has precisely 2 distinct points in common with that circle of inversion shown in white, then under the inversion of the plane with respect to such a circle, that red circle will be taken into a straight line that will be located on the same side as the pre-image circle, and that straight line will not pass through the center of inversion, but it will have precisely 2 distinct points that are in common with the circle of inversion, and these will be these 2 points right here. When the power of inversion will be negative, then in this case, the image straight line will be located where? Well, it will be located on the other side of the pre-image circle with respect to the center of inversion, but it will pass through what? Through diametrically opposite points that are shared between the given circle and the circle of inversion, and so on. For example, if our pre-image circle passes through the center of inversion and has precisely 1 point in common with the given circle, which means that it is tangent to the given circle of inversion internally, then that circle will be taken into a straight line, which will shown over here. It will be tangent, 1 point in common. When the power of inversion is positive, when the power of inversion is negative, and we have our circle, it will be taken into a straight line that will also be tangent to the circle, but the tangency point will be the diametrically opposite image with respect to this one. Likewise, when we will have a circle that has precisely 0 points in common with the given circle of inversion, but it passes through the center of inversion, it will be taken into the corresponding straight line on the same side or the opposite side. When the power of inversion is negative, the side will be opposite over here, and when the power of inversion is positive, it will be on the same. Negative the other side, positive power the same side. Think about the proofs of these theorems. Like I said again, I will go over a proof of just one such theorem in great detail, and you will be expected to generate the proofs of the remaining theorems on your own.